Okay, so what we want to talk about now today is we're going to be talking about the invertible matrix theorem. And we're going to be looking at the first part of the invertible matrix theorem because we've only really gone through work with systems of equations, matrices, and augmented matrices. And so the invertible matrix theorem actually extends out into work with vectors, and it extends out into working with linear transformations. And it's a very wide and sweeping theorem that happens to connect a lot of the downline of linear algebra. So when we talk about that this is part one, what we're talking about is for this first part where we're looking at systems of equations, vector equations, matrix equations, okay, and the like. All right, so with that stated, what we want to do is we want to say, okay, well, let's take a look at this particular theorem and then see how it connects together all of the ideas that we've gotten with systems of equations. So let's start out with first the statement that let A be an n by n matrix. Okay, and so you have to remember that A must be square. Okay, so A must be square, and we talked about that in an earlier lecture. And then we've got this statement: the following conditions are equivalent. And what we mean by equivalent, or what is meant by equivalence in mathematics, is that each statement, if I have one of the statements, I have all of the statements. That means that if I know that the rank of A is equal to n, and A is an n by n matrix, by the way, always has to be square, then I know everything else. I know that A is invertible. I know the equation AX equals B has a unique solution for all B. I know A is row equivalent to IN. So I know all of these things, and it's actually a really, really handy thing to know. I mean, like, because it basically tells you, oh, A is invertible, boom, I'm done. Okay? So, with that stated, that's what we mean when we say that the following conditions are equivalent. Now, from a math perspective, that means that we've basically got to prove in both directions. So that means that if I prove that A is invertible implies that the equation AX equals B has a unique solution for all B, then I've got to actually prove it in the opposite direction. And we did that in a bunch of earlier lectures where we talked about in this case, the invertible matrices. We talked about this when we talked about, say, for example, elementary matrices, and how those worked. And we talked quite a bit about it when we talked about things being row equivalent, or matrices being row equivalent. So what I'm going to do is I'm going to go over big picture ideas here in this, and I'm not going to do as much proving. If necessary to do some proving, I will. But like I said, I'm going to kind of stick to the big picture ideas. All right. So first, let's take for example, let's say for example, if A is invertible, then AX equals B has a unique solution for all B. Okay. So like, let's say for example, if A is invertible, then AX equals B has a unique solution for all B. So we start out with let A be invertible. Okay. And what we showed a little bit earlier, and this is kind of a great review to think about how invertibility really matters, we'll have AX equals B. Then we have A inverse A X equals A inverse B. And that's only because A inverse actually exists. Since A is invertible, we have an actual A inverse, okay? And then that gives me that X equals A inverse B, because A inverse is simply just the identity, okay? The identity on N for n by n matrices. Now, why something like this is so powerful, okay, is to notice that that is in fact going to be unique, because what we say is that matrix multiplication is well defined. So A inverse B, okay, is the same every time I multiply it. So that makes X unique. And that's basically the idea behind this. And so hence, okay, AX equals B has a unique solution for all B. Ta-da! Great. That's actually really great. That's cool. Okay. Now, what that extends, how we can extend that idea is to say, well, let's say if A is invertible, right? We want to prove AX equals 0 has only the trivial solution. So the first thing that I'm going to say is that, well, we're going to let A be invertible. Okay. So we're going to state that first. Here's our proof. Then what we've got here is that A times 0 equals 0. Okay. As this is always true. That's actually trivially true. Multiply a matrix by the 0 vector, you're going to get back the 0 vector. Okay. So that is a solution to AX equals 0. So this is a solution to AX equals 0. But by our theorem above, okay, because A is invertible, okay, because A is invertible, AX equals 0 has a unique solution, right? That was the statement from the previous one. And so the trivial solution, x equals 0, is the only solution. Is the only solution. All right? Now, by the way, these are more explanations than they are rigorous proofs, but the fact of the matter is I'm really interested in kind of an explanation and an understanding of the relationships that are existing between the solutions to systems of equations and invertible matrices. Okay, so now what I'm going to say is, okay, well, what happens now if, say, for example, the rank of A equals n? Okay, so let's say, for example, that the rank of A equals n, and I want to show that A is invertible. So let's say, for example, here, we'll take another one. If the rank of A equals n, then A is invertible. And this is actually going to help us out, right, as we start to talk about, the other things. If the rank of A is equal to n, then AX equals B has a unique solution. We actually have a direct proof from that. We did that earlier. But let's start out with this one. The rank of A equals n, and then A is invertible, all right? So if the rank of A equals n, then there is a pivot in every row of RREF A, okay? So basically it has no 0 rows. So if we think about this, what we're going to end up getting, right? Let's take an example. Suppose here's an example. Suppose A is, let's say, 3 by 3. All right. So the RREF of A, okay, is going to equal this. Okay. So the RREF of A is going to equal this. And what you're going to notice is well, look at the rank. So the rank of A is equal to 3 because we have 3 non-zero rows. And the way you know you have 3 non-zero rows here is because you've got a pivot, right, in every row. Right? There's actually a pivot in every row of the RREF. Or you can use the row echelon form. There's a pivot in every row of the row echelon form as well. Okay? So, if that's the case, then there are n pivots. Okay? So now we've got n pivots. So like if you think about this, well, that makes sense, right? If you have a pivot in every row, okay, then you're also, that means that you're going to have n pivots. That makes sense. Okay, there you go. This means, okay, that we have pivots in n columns as well. Right? So basically what that's saying is that if you have pivots in n rows, you're going to have pivots in n columns, right? I mean, makes sense, right? 1, 2, 3. Yes? And so since you have pivots in n columns as well, well, here's the thing. Since there are n columns in A, we have a pivot in every column. Okay? Kind of makes some sense. All right, so we have a pivot in every column. And this should be said, it's of RREF of A. Okay? Thus, A row reduces to the identity. All right? Ooh, that's kind of nice. It's handy. Now, inside of the book, inside of an earlier section, what I did was I actually went in and showed that because the rank of A is equal to n, we end up having a unique solution for all AX equals B. And since we have a unique solution for all AX equals B, then what we end up with is we end up with a A being invertible, and that's how we ended up getting to invertibility. In this case, I'm going to actually add some pieces here. I'm going to show that we can actually go around in some different ways, right? We can, that all of these statements are in fact connected and that you can in fact prove each one in different directions, sometimes some easier than others, okay? So it row reduces down to the identity, and so wouldn't it be handy, right? Wouldn't it be great to know that if A row reduced to the identity, then A was invertible. Okay? Yeah, that would be really great. Well, we talked about in an earlier section, we know that, so we know that if A can be expressed as a series of elementary matrices, then A is invertible. Okay, then A is invertible. Well, so what we're going to do is we're then going to use that information in order to help us to get to from A is row equivalent to the identity to A is invertible. So let's say, for example, so we know now that A row reduces to the identity. So let's say, for example, A is row equivalent to IN. Okay, let's say it's A is row equivalent to IN, which was the sixth statement that we had in the invertible matrix theorem. So if A is row equivalent to IN, then, okay, A can be row reduced. That's what it means to be row equivalent. A can be row reduced to IN. Thus, there exists elementary matrices E1 through EN such that, okay, because we could transform every row operation into an elementary matrix, so such that we have En E times E to the n minus 1 times dot 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 E2 times E1 A is equal to the identity, okay? Or is equal to IN. Now, each one of these elementary matrices, since each elementary matrix is invertible, okay, we established that earlier, then, okay, we could take the inverse of all of them, right? Another statement that we got A, okay, equals IN. And then what I'm going to do is I'm going to take the inverse on both sides. So this is EN, E to the n minus 1, all the way to E2 times E1 inverse. And I'll do that to both sides. So actually this will then be EN dot 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 all the E2 times E1 inverse A, okay? Inverse I, excuse me, inverse I. So A equals basically E1 inverse times E2 inverse times E3 inverse all the way down to En inverse, all right? And so in this case, A can be written as a series of elementary matrices because each matrix E1 inverse is also an elementary matrix. So the inverses of elementary matrices are also elementary matrices. That's actually kind of a really important point. Okay, so the inverse of each elementary matrix is also going to be an elementary matrix. Excuse me. So yeah, nice. Okay. Now, what we're going to want to do then. Okay. So what does that mean? Well, if A can be written as a series of elementary matrices, earlier on we showed that means A is invertible. So thus, A is invertible. Yay. It's nice. Now that we just actually proved a bunch of things here, okay? One is we showed that the rank of A, right? We showed rank of A equals N implies, okay, A is invertible. We also showed two that if A is row equivalent to IN, then A is invertible. There's another one. And we discussed, right, from a previous section, that if A is the product of elementary matrices, then A is invertible. All right. So that's actually like hey, that's kind of handy. It's handy to know all those things. Now, like I said before, they go backwards and forwards. That's what it means for these guys to be equivalent. Yes? The other thing about these statements, right, these statements here that I have to be equivalent, is if these statements are equivalent, it means their negations are also equivalent. So what that means for us is this. If A is not invertible, then the equation AX equals B does not have a unique solution for all B. There exists, right? There will exist AB, right? That does not, where we have AX equals B, does not have a unique solution. Either A, it does not have a solution, or B, that solution, it has an infinite number of solutions for that particular value of B, okay? Or if I know that, for example, the equation AX equals 0 does not have the trivial solution, that tells me that A is not invertible, right? There it is. And specifically, if A is not invertible, then ax equals 0 does not have the trivial solution, right? Or if I know that the rank of A is equal to something other than n, right? Okay, if the rank of A is equal to n minus 1, or the rank of A is equal to n minus 2, then that also tells me that, in fact, I don't have an invertible matrix. It also tells me that Ax equals 0 is not going to have a trivial solution, right? So, like, for example, I'll give an example um, of how we use something like this, right? So suppose A is n by n, and suppose the solution to Ax equals 0 is, and we'll write it as x equal to, I'll write it as an equation. Let's say x equals t negative 1, 3, 1. Okay, so we've got t negative 1, 3, 1, right? Now what you notice about this is that, so what we see is that the solution to Ax equals 0 is not the trivial solution. So we're going to say, so the solution, oh, I should probably ask, what am I asking, right? Okay, is A invertible? So the solution to Ax equals 0 is not the trivial solution, right? It actually, in fact, has an infinite number of solutions, okay? So, by the invertible matrix theorem, A is not invertible. Okay, there it is. Let's try another one. All right, suppose, okay, that A is 3 by 3, okay, and the rank of A is equal to 3. What is the solution, okay, to Ax equals 0? And is that solution unique? All right, well, A is 3 by 3, so A is square, and the rank of A is equal to 3. So, okay, since the rank of A is equal to 3 and A is square, by the invertible matrix theorem, Ax equals 0 has only the trivial solution. So, 0 is the solution, and it is the only solution. And that's how we use this idea of equivalence, right? Notice in this one, I said that A is 3 by 3 and the rank of A is equal to 3. And I asked, what is the solution to Ax equals 0, right? And is that solution unique? Well, according to the invertible matrix theorem, I don't even need to say that A is invertible. I can if I want to, but I don't need to. What I need to say is that I know that I'm going to have only the trivial solution, right? It's the only possible solution that I can have to Ax equals 0 since, right, I have that rank of A is equal to 3, right? Look, 3 by 3, that's the matrix size, and the rank of A is equal to, in this case, n, so consequently, I get the third one automatically. That is, the equation Ax equals 0 has only the trivial solution. And there we go. And that actually kind of extends what we need to know about, um, That's how we use the invertible matrix theorem in order to tell us things about matrices that we may not exactly have the matrix, but we know something about it, right? Or even that we know even just a little piece about it, right? Okay, and it kind of helps us to think about these issues with matrices. All right, so that's the invertible matrix theorem in a little bit of a nutshell. Go back into either the book or into the videos and take a look at the proofs for each one of these, going backwards and forwards. It'll kind of help you out to think about what each one of them means. All right, and take a look at the examples that we went through in just a minute ago in order to kind of help you understand how we might use the invertible matrix theorem in order to help us do mathematics.